In this video, we will be discussing on the acceptance angle and numerical aperture of fiber optics. In our previous video, we have discussed about the propagation of light in optical fiber. So today we'll find out the critical angle of propagation first. Now for this, let us consider a step index optical fiber. So what is step index optical fiber? A step index optical fiber is a fiber where the refractive index changes abruptly at the core cladding interface. So we have considered two rays here. The two rays are shown here. One is a solid line, blue line, and another one is the dotted line. So the solid ray, that means this blue one, it undergoes refraction at the point A, and it propagates at an angle theta c in the fiber. So it makes an angle theta c with the axis of the fiber. Now since n1 is greater than n2, this ray undergoes total internal reflection at the point B on the core cladding interface. So you can see here it is making an angle phi c here. Now let us take this angle as phi c. So from our previous calculation we have seen that phi c is equal to sine inverse n2 by n1. Now this ray which is incident at an angle larger than phi c, if there are certain rays, if they are incident at an angle larger than phi c, they will be confined to the fiber because they will be totally internally reflected. So if a ray is incident at an angle greater than phi c, they will be totally internally reflected inside this core and it will propagate in the fiber. Now, the ray incident at the core cladding interface at this critical angle, this ray is known as the critical ray. So, the ray which is incident at this critical angle of incidence is known as the critical ray. Now, this critical ray makes an angle theta c with the axis of the fiber. Now, the rays with propagation angle larger than theta c will not propagate in the fiber. So, the rays which be larger than theta c, they will be, you can see here, they will be lost in the cladding. So, from this diagram, you can see, let us take this triangle A, B, and C. AC by AB is sine phi c. We have two angles here in this triangle, phi c and theta c. So sine phi c is AC by AB and cos theta c is also AC by AB. So that means these two are equal. Sine phi c is equal to cos theta c. Now from our previous calculation, we know that sine phi c is equal to n2 by n1. So cos theta c will be equal to n2 by n1. So in that case, theta c, that means this angle, which is also known as the critical angle of propagation, this theta c, which this ray makes, critical ray makes with the axis of the fiber, this theta c is equal to cos inverse n2 by n1. So remember, theta c is equal to cos inverse n2 by n1. Now let us now discuss about this acceptance angle. Now for this, let me take the pen first. Okay, so here we have the three medium. Now one is the this launching medium. So this launching medium has a refractive index n0. And this core, we have taken the refractive index n1, as we have previously already said that, and the cladding, the refractive index is n2. Now let us apply here the Snell's law. So here what will be, if we apply Snell's law, it will be n0 sine theta I. So this theta I, this theta I is the angle which the incident ray is making with this axis of the fiber, and this is theta r, that is the angle of angle of refraction. So sine theta I into n0 sine theta I will be equal to n1 sine theta r. So we can write here sine theta I by sine theta r is equal to n1 by n0. Now you see here, if we increase the value of theta I, if we increase the value of theta I beyond a certain limit, this angle phi, this angle phi, this angle phi will, what will happen? It will drop, it will decrease, and after a certain time, uh, beyond this limit, what will happen? This critical value, this phi will drop below the critical value phi c. Now, if this for a certain rate happens, then that ray will not be undergoing total internal reflection. Then that ray will escape through the cladding. That will not take part in the propagation. So in that case, there is a maximum limit for theta I. So if we take the largest or the maximum value of theta I, so that occurs when phi is equal to phi c. So when phi is equal to phi c, theta I reaches the maximum value. So theta I is equal to theta I max. So for the triangle ABC, so if we take the triangle A, B and C here, sine theta r is equal to what? Sine 90 minus phi, which is equal to cos phi. So this is equation number 1 and this is equation number 2. Now from these two equations, what we get? Sine theta I is equal to n1 by n0 cos phi from equation 1 and 2. Now when phi equal to phi c, as I have mentioned, this theta I has a maximum value. Let us take this as theta A, where theta I reaches its maximum limit. So sine theta A is equal to n1 by n0. So we are replacing here in this equation. Sine theta A will be equal to n1 by n0 cos phi c. Cos phi c. Now we know that from our previous calculation of total internal reflection that sine phi c is equal to n2 by n1. So we can easily find out the value of cos phi c, which is root over n1 square minus n2 square by n1. Now this is equation number 3, this is equation number 4. So from these two equations, if we combine, we can get the value of sine theta A. So sine theta A will be root over n1 square minus n2 square by n0. So this is the value of sine theta A. Now if this launching medium, is air, then our n0 will be equal to 1. So if we put n0 equal to 1, the equation becomes sine theta A is equal to root over n1 square minus n2 square. So this angle theta A is called the acceptance angle of the fiber. This theta A is known as the acceptance angle of the fiber. So what is acceptance angle? Acceptance angle is defined as it is the maximum angle of incidence that a light ray can make with the axis of the fiber so that it may propagate through the fiber. Okay, rays that are incident on the face of the fiber making angle less than theta A will undergo repeated total internal reflection and will reach the other end of the fiber. So obviously, larger acceptance angle makes it easier to launch light into the fiber. So this theta A with the semi-vertical angle theta A, the cone which is formed here is known as the acceptance cone. So what is acceptance cone? The light rays content in the cone having a full angle 2 theta A are accepted and transmitted through the fiber. So this cone is known as the acceptance cone. So the light rays which are falling inside this cone, which are incident inside this cone, they will undergo total internal reflection in the fiber and they will propagate through the fiber. Otherwise, those rays which are falling outside this cone, they will be refracted and will be lost in the cladding. So this cone is known as the acceptance cone. Now, the numerical aperture is a is the determines numerical aperture determines the light gathering ability of the fiber. So you see here the numerical aperture is defined as the sine of the acceptance angle. So na is a numerical aperture, it is sine. Theta a is the acceptance angle, so sine of theta a. So numerical aperture is equal to sine of theta a. Sine theta a is root over of n1 square minus n2 square. So numerical aperture will be root over of n1 square minus of n2 square. Now you see here n1 square minus n2 square, we can rewrite it as by using the mathematical formula n1 plus n2, n1 minus n2. Okay, so we can rewrite it as n1 plus n2 by 2. So we also put a 2 here in the numerator, and n1 minus n2 by n1, and we put this n1 again here in the numerator, and we rearranged it in this manner so that we can approximate n1 plus n2 by 2 as n1 and n1 minus n2 by n1 as del. So this del is the fractional refractive index change. So we can rewrite n1 square minus n2 square as 2 n1 square into del. So the numerical aperture becomes root over of 2 n1 square del, that is n1 root of 2 del. Now you can see here that this numerical aperture is basically dependent on the refractive index of the core and the cladding of the material, and it does not depend on the physical dimension of the fiber. So numerical aperture determines the light gathering ability of the fiber. It is the measure of the amount of light that can be it is a measure of the amount of light that can be accepted by the fiber. So typically the value acceptance angle is of theta less than 30 degree. When it is theta is less than 30 degree, the numerical aperture has a value less than 0.5. So if the numerical aperture is very large, it implies that the fiber will accept large amount of light from the source. So this is all about the acceptance angle and numerical aperture. Thank you all.